All right, so this is going to be the video for section 3.1 in differential equations. This is part of the modeling unit, and in this unit, we're going to cover sections 3.1, 3.2, and 5.1. This covers everything that we're going to cover in this first part of the course here about using differential equations to do calculations related to real-world scenarios, right? So this is more where it kind of gets back into concepts and not just so much algebraic manipulation. So hopefully you'll find this section interesting. This first section on 3.1 is going to just use models where we can use differential equations which involve first-order linear differential equations. So first of all, the word modeling means to find a differential equation that somehow models a scenario, right? And then typically we'll solve that differential equation, and then we'll use the solution curve to answer some questions about the scenario, right? Differential equations can be used in many different scenarios. So in this course, we're going to focus on some of the most common and also, I think, some of the most interesting applications, but they're useful in a very wide variety of scenarios. You can take an entire course just in modeling with differential equations in college. So we'll only be able to kind of scratch the surface here. Okay, so the first thing we're going to consider is growth and decay that's proportional to amount. So there's a lot of situations in the real world where the rate of change of a quantity with respect to time is proportional to the current amount of that quantity. In problems like this, it would be appropriate to use a differential equation like this, like dy dt, the rate of change of the quantity y, how fast y is changing, is proportional to the current amount of that thing, right? So if you have dy dt equals ky, where k is a constant of proportionality, then that means that the smaller the amount, the less change there'll be. And when you have a large amount, there'll be a large change. And many things behave that way. In fact, three specific examples from the real world. One is unrestricted population growth. So if you have, let's call the y variable p for population, t for time is the x variable. Okay, what this is saying is if you have a population, how fast the population is growing is proportional to how big the population currently is. So for example, imagine if you had, say, rabbits, and you had a small number of rabbits. Okay, so you have a few breeding pairs, right? And that means that how fast the population is growing is going to be fairly small. But if you get to the point where you have a large number of breeding pairs of rabbits, large population, then there'll be a very rapid increase per unit of time in the population. So the rate of change is proportional to the population. Another place this shows up is in continuously compounded interest. So if you put money into an investment and it compounds continuously at a constant rate, then the same thing is true. You have an amount of money in the account, and then how much that is changing, which is the interest, is proportional to the amount. So if you have a small amount, you get a little bit of interest. If you have a large amount, you have a large change in the interest, which represents the change in the amount. It also is true for radioactive decay. Radioactive decay is the idea that you have some sort of a substance which is radioactive. So as just sitting there on the table, it will just spontaneously eject a particle every once in a while, right? And what that means is that the amount of mass over time shrinks, right? At some point in the future, you've got less mass because it just keeps throwing parts of it away, right? Well, it turns out that at first, right, when you have a large amount of material, there's a large amount of molecules to eject. So you have a large amount of change in uh, at that point when this is large. But when you get down here to where you have a small amount, you have fewer particles. So you have fewer particles that can be ejected. So the rate of change drops as the quantity drops. So unrestricted population growth, continuously compounded interest, and radioactive decay are all situations that can be modeled by a first order linear differential equation. And it's just some form like this. The derivative is equal to some constant times the quantity of the y variable. Okay, so let's look at a specific example here, and we'll actually go through the solution process. Let's say that we have some sort of compound interest thing where you have dA dt is equal to a constant times a. Okay, this particular form can be solved by separation of variables. So we could move the dt over to this side and divide both sides by a to get 1 over a dA equals k dt. And then we would take the integral of both sides to find the solution. So we would get the natural log of the absolute value of a equals kt plus an integration constant. And then if we wanted to solve that explicitly for a to get an explicit solution, we would take e to both sides here, which this could be separated into e to the kt times e to the c1. And then that just itself is a new constant. So I'm just going to call that C. So the amount is equal to a constant times e to the kt. This is the solution. And this is the general solution, right? But if I have an initial condition, like when time is 0, the amount is some value that we call a sub 0 for the initial amount. If you plug that amount in for the a and 0 for the time, you'll get that this constant is indeed the initial amount. So that gives us a particular solution for the scenario. The amount is equal to the initial amount times e to the kt, right? And that might look familiar to you. A equals p e to the rt. That's where this formula comes from that we just memorized back in Honors Algebra 2. It's the solution to this differential equation, right? So any sort of a growth or decay kind of problem that can be expressed like this, its solution is going to be of the form y equals some initial value y times e to the kt, right? And that'll always be true. So sometimes you have standardized forms like this that you can jump straight to the solution. And in other cases, when we do our modeling, it won't exactly match something that's standardized. So we'll have to go through every time and solve the equation by hand. Okay, and sometimes the constants involved have meanings and sometimes they don't. In this case, this particular integration constant has a specific meaning. It means the initial amount in the account. And actually this K has a meaning too because it happens to be the annual interest rate or the interest rate over whatever time period this T is covering. Sometimes the constants have meanings and sometimes they don't. Okay, then we could ask specific follow-on questions. We could say something like, at what point would the amount triple? Or when would you have $3,000 the account if the initial amount was $50 or something like that? So let's take another example that's a similar form, and we'll use the result to answer the question here. Let's say we have a culture initially contains 200 bacteria. At 1 hour, the population of bacteria has increased to 300 bacteria. If the rate of growth is proportional to the number of bacteria present, which makes sense because each bacteria divides, right? So the more bacteria you have, the faster the population is going to grow. Determine the time needed for the bacteria population to quadruple specifically. All right. So, well, we've got our equation here. This is exactly the same form as the one we just solved, so I could jump right to the solution. The solution is going to be of the form that the population is equal to some initial population, e to the kt. And because they told me that we initially had 200 bacteria, they're telling me when time is 0, the population is 200. So since I know this particular constant has a meaning, I'm just going to slot that 200 right in there. But then for me to solve for this other unknown constant k, I'll need another initial value essentially, right? So I'll have to have something like when time is 1, population is 300. So you can plug in the population and the time value and then solve this, divide both sides by 200, right? And then so that means we have e to the 1 times k, e to the k equals 3/2. So then to untrap the k from the e, we take the natural log of both sides. So you get k is equal to the natural log of 3/2, which is some decimal. And then if we fill that in, we have a model. Now we have a model, which is the solution to our differential equation model. So the population is 200 of bacteria is 200 times e to the 0.405 t. And then we can use that model, the solution curve, to answer other questions like how long will it take to quadruple? So a quadrupling would be that the population is now 4 times the initial 200. If you divide both sides by 200, you get 4 here. And then you can again use a logarithm to solve for t, which t turns out to be the natural log of 4 over 0.405465, which is 3.419 hours. So that's the basic idea. So we've been doing things like this certainly back in brief calc and even before. I remember doing problems when I used to teach Honors Algebra 2, back when it was called Honors Algebra 3-4. We did problems like this. You just think of what we call now initial conditions as like data points. And anytime you have a constant, you have to use a data point to establish that constant. Right. So the only thing that's new now is that we may start from a differential equation to derive the equation that we're then using as the solution, and then resolving the constants and then using that to answer a question. So a lot of this is stuff that you've seen before, but we're going to look at some additional kinds of standardized models as well. So while we're on the subject of radioactive decay and populations that are modeled by this particular structure, let's talk a little bit about radioactive carbon dating. So this is an interesting application. In 1950, a chemist named Willard Libby found a way to use the ratio of the amount of radioactive carbon-14 to ordinary carbon in a living substance to establish the time when it died. So it turns out that cosmic radiation in the atmosphere acts on nitrogen molecules, and our atmosphere is mostly comprised of nitrogen. And it turns some of that nitrogen into regular carbon and some into radioactive carbon-14. So the action of cosmic radiation on nitrogen causes chemical reactions which produce a radioactive isotope of carbon called carbon-14. And this ratio of radioactive carbon-14 to regular carbon is constant around the atmosphere of the Earth. And it gets absorbed by all living things, right? Because living things breathe the air, right? So it's present in the air. And we also eat things, and it's present in all of the plants and then the animals that eat plants. So within our own bodies and anything that's alive, there's a ratio of radioactive carbon 14 atoms to regular carbon atoms. Now, once an organism actually dies, then the absorption of the radioactive carbon by either breathing or eating stops, and that means that you start out with the ratio, the normal atmospheric ratio of radioactive carbon-14 to carbon in your body. Okay, but since you're no longer eating and breathing, the regular carbon remains in your tissues, but the radioactive carbon-14 decays over time. So what you can do is use the fact that we know that the half-life of carbon-14 is that when you go 5,600 years, whatever the amount of carbon-14 was in your system, you'll be down to half of that amount. So that wasn't a very good graph. You'll be down, let me draw that over again. We know something called the half-life, which is how much time it takes for half of it to decay. So if you start out with you have some initial amount of carbon-14, there will be some point when you're down to half of the amount you had at the beginning. And that time is called the half-life, which for carbon-14 turns out to be 5,600 years. Okay, so we can tell from the ratio how much carbon-14 there was and how much carbon-14 there is, and tell where we are in this curve. Let's do a specific problem so you can see how it works. A fossilized bone is found to contain 1,000th of the carbon-14 level found in living matter. Okay, so they found that by comparing the levels to the levels in bones if an object was alive, which they know. Okay, estimate the age of the fossil. So we can use this form of the differential equation that the rate of change of the carbon-14 quantity is proportional to the amount left. By separating variables, we can come up with a solution, which is like A equals P e to the RT, except we just have different names for the constants. The Y variable is called Q now. We're going to use initial conditions to establish the constants. Now, we don't know what this constant is. We would have to know what the quantity was at time zero, which we don't know. But I do know that when time is 5,600 years, we're down to half of the initial quantity. So if I plug half the initial quantity in here and 5,600 years in for the time, right, we can divide out the initial quantity. We don't need to even know that. So E times 5,000, E to the 5,600K has to equal a half. So if you take the natural log of both sides and then divide by 5,600, you can establish that this K constant is negative 1.23776283 times 10 to the negative fourth, a very small number. And if we're doing a carbon-14 problem, we want to use as much accuracy as possible here because it's very sensitive to this constant. So we can fill that in. And now I have a model that says if I can figure out what percentage of like plug in a percentage of the remaining time here and divide out the Q0, I can solve for the time, right? So the question is, if we are down to 1/1000th of the quantity, like in this fossilized bone, then how much time has passed since the time that it died? So this right now is 1/1000th of the initial quantity. So if you plug 1/1000th of the initial quantity in and divide out the Q zeros, you can solve this by taking the logarithm of 1/1000th and then dividing by the constant. So when you do that, you end up getting 55,800 years or so. Okay. Now, there is kind of a practical limit to carbon dating, and this is kind of near the upper edge because of how sensitive it is to this constant. But up to around 50,000 or maybe even 100,000 years, this method is considered fairly accurate for dating. I don't think I would report the 8 here, maybe about 55,800 or maybe even about 56,000 years would be appropriate. Okay. Anyway, the solution to this differential equation allows us to determine the age of anything that was alive. For example, you can determine when an object was alive, say in Egypt, if there was writing on papyrus scrolls, right? Because papyrus is made out of plant material, and plant material is alive, so it's subject to radioactive decay. And you can figure out the age of paper and the age of bones and the age of any kind of tissue or any plant material, right? This way. Very interesting. Okay, so let's take a completely different tack. Here's another situation that's modeled with a first order linear differential equation. It's called Newton's law of cooling and warming. So if you have an object that starts at one temperature and then it gets immersed in a medium that's at a constant temperature, then we can model how the temperature of the object changes over time. Okay, so you have to make the assumption that the medium is large. It acts as what we call a heat sink, which means that it can either absorb or give off an infinite amount of heat energy without its self-changing temperature. So imagine that, like say, you immersed an object in a vat of oil, and that oil is so large that even if there's a temperature differential, whatever you put in that object is not going to either heat or cool up the oil, right? It'll be a negligible amount, but the object itself will change temperature, right? So if that's true, then you can model this with this equation. You can say this was invented by Isaac Newton, and it's Newton's law of cooling. It says that capital T is temperature and little t is time. The rate of change of temperature over time, how fast temperature is changing, is proportional to how far away the object's temperature is from the medium's temperature. So if you take the difference, right, then that means if the temperature is currently above the temperature, right, then the rate of change will be, well, this constant will turn out to be a negative number because it will drop. So think about it. If you immersed an object into a medium and it was exactly at the same temperature, this would be 0. So there'd be no reason for the temperature of the object to change. But the further away this temperature is from the medium's temperature, the faster the temperature moves to try to get closer to that equilibrium temperature of the medium temperature. Okay, so if we wanted to solve this differential equation, we could put this in standard form by multiplying this out and then moving the t term to the other side. So it'd be dt minus kt equals minus ktm. This is a constant, so this is just a constant over here. So this is a linear first order differential equation with temperature as the dependent variable. That means we can identify this right here as our px, or in this case, it's pt. And then we can use an integrating factor. So it's e to the integral of px dx, which in this case is integral of just minus k dt. So that would be e to the negative kt. And the idea is then if you multiply the variable times that, the y variable times that, and then the right-hand side times that, the left side is the derivative of the answer. So you take then the integrating factor times the y variable is equal to the integral of the right-hand side times an e to the kt times the integrating factor. So this k and this tm are constants, so they come outside. The antiderivative here is just the copy e to the negative kt divided by the constant negative k. So this will cancel out. And then you get, at this point, you have e to the negative kt t equals tm e to the negative kt plus c. So if you divide now both sides by this e to the negative kt, this is a c here, divided by e to the negative kt, this cancels, and so you're left just with tm plus c, and then if I move this to the top of the fraction, it becomes e to the positive kt. So this is the solution format for a Newton's law of warming or cooling problem. So I won't have to necessarily solve that again. I'll just be able to go straight from here to here, just like the solution of this equation turned out to be equal to a equals a0 e to the kt, right? So this is a different form. This differential equation has this solution form. Okay, so let's look at that in action. Um, Here's a specific example where we actually have to use this model twice with two different differential equations. At time t equals 0, a sealed test tube containing a chemical is immersed in a liquid bath. The initial temperature of the chemical in the test tube is 20 degrees C. The bath has a constant temperature of 90 degrees C. After 2 minutes in the bath, the test tube temperature has risen to 30 degrees C. After remaining in the bath for 10 minutes, the temperature is taken out of the bath and then kept in a room whose ambient temperature is a constant 40 degrees C. After 5 minutes in the room, the test tube temperature has decreased to 50 degrees C. How long, measured from the start of the entire process, will it take for the temperature to reach 45 degrees C? Okay, in this problem, there's actually two parts. There's the time that it's in the liquid bath and the time that it's in the room air, right? So for each, the differential equation is of this form, which means it's going to have this solution form. So we're going to use this solution separately on the liquid time and the air time. So let's do the liquid first because that came first, right? We know that this Tm is the medium temperature. So the temperature of the test tube is going to be equal to 90 plus some constant E to some other constant T. And we know that when time is 0, the test tube started at 20 degrees C. All right, so if I use this as an initial condition, then I can plug the 20 in here, the 0 in here, and solve and find that C is negative 70. So that means that now I know that T is, the temperature of the test tube is 90 minus 70 times E to the KT, but I still have another constant to deal with. So I need another data point, another initial condition. And so they told me that after 2 minutes in the liquid bath, the temperature is now 30. So if I plug 30 in there and 2, I can solve for K. It'll involve taking a logarithm here. First, you would maybe move this to the other side and subtract the 30, divide by 70, then take the logarithm of that 6/7, and then finally divide by the 2 to get that this constant is negative 0.077075. Right? This constant should be negative because if you think about it, if the temperature was above the medium, then that means that the rate of change would have to be negative. So this constant should always be negative in a heating and cooling problem, because if this is negative, it will cause this to get closer to the medium temperature, right? So it's right that this is negative. So when I plug it in, here's my final model for the liquid bath portion of this problem. And then it says that it stays in the bath for a total of 10 minutes. So if I plug in 10 to the time, I can compute that the temperature right at the moment when we take it out of the bath to put it in the room air is 57.6 degrees Celsius. Okay, then we have to now do a new differential equation for the room air time because it has a different medium temperature. Now the temperature of the medium is 40. So we've got that same structure, right? And I'm going to do something to keep things simple. I'm going to redefine t equals 0 at the start of this part. So it's a separate t variable, okay? All right, and then that means that the initial time at the beginning of this phase is the ending temperature of the liquid phase, so 57.6. So that becomes the initial temperature. So if I plug that in here and 0 for the time, I can solve for the C constant and get 17.6. So now we know that the temperature is 40 plus 17.60 to the KT, but I have this unknown constant here, the proportionality constant. So we have to have another data point, and we do. It's told in the problem that after 5 minutes, the temperature is now 50. So when we plug 50 in and 5 for the time, we can solve for that K. And that K ends up being negative 0.11306. So finally, I have this model for my solution for the room air portion. Okay, so then the final question was, how long from the start of the process does it take until the test tube temperature is 45? So I can now plug for the room air part 45 in and then solve for the time. Right, so you subtract the 40, you divide by 17.6, take the natural log, divide by the constant, and you get that the time would be that it has to spend 11.1 minutes in the air. But because it also spent 10 minutes in the bath, that means there's a total of 21.1 minutes since the beginning of the process started. Okay, so there's a differential equation usage to be able to model a reasonably complicated multi-stage cooling and warming scenario. All right, kind of interesting. So whenever you see that there's a clear change in the state in the conditions, like going from liquid to air or something like that, you would want to break it into two different parts, each with its own differential equation, each with its own solution, and then link them up by making the end point of the first scenario be the initial point of the second scenario, assuming they're occurring in sequence in time like that. All right, let's keep going here. Another use for first order linear differential equations is very simple series electrical circuits. So electrical circuits can be very complicated to solve, but we can look at some simple ones and actually apply things even with first order linear differential equations. In electrical engineering, a circuit is an arrangement of circuit elements that are connected in series, one like in a line, like if you lined them up and connect them together, the start of one to the end of the other, right? And the circuit then starts at the positive terminal of a voltage source. It goes around through the circuit elements, and then it ends at the negative terminal of the voltage source. So it makes a complete circuit, right, with no breaks. Okay, the response to applying a voltage to the circuit is that a current flows through the elements of the circuit. And what current is the flow of electrons. So electrons form what's called electric charge. And when electrons are flowing or electric charge is flowing, that creates something called current. So a lot of terminology related to electrical stuff. And this is talked about in the book. So I'm just sharing stuff in the textbook here. But I'm going to add on to it some additional terminology here from being an electrical engineer myself. There are three general types of electrical elements. One is called a resistor, one's called an inductor, and one's called a capacitor, or the old name for a capacitor is condenser. So if you ever talk to a mechanic, like an airplane mechanic or an auto mechanic, they might refer to a condenser. That's another name for a capacitor. All right, so what is a resistor? A resistor is usually made of some partially conductive medium like carbon with other materials mixed in to control how well it conducts electricity. So resistors simply resist current generation from an applied voltage, and they behave according to something called Ohm's law, which says E, which stands for the electromotive force, which is the voltage, is equal to the current times the resistance. Okay, so E is voltage. That's given in the units volts. The I is the symbol that we use for current, and it is measured in amperes. Actually, that should be a capital A because it's named after someone. And then the R is resistance, which is measured in ohms. Okay, the symbol on a circuit diagram looks like this. It's like a kind of a jagged line for the resistance, and then this is the start and end where they connect into the circuit. Okay, an inductor is another kind of circuit element, circuit element that is made of a coil of wire. If you look at a wire, whenever current flows through a wire, because of Maxwell's equations, which are based on partial derivatives and curl and divergence that we studied in Calc 3, you can show that current moving through a wire will generate a radiomagnetic field. So if current is moving through a wire, it will generate a magnetic field like this around the wire. Okay, and so what a coil does is it tries to put the wire into an arrangement here so that the magnetic field from one coil is affecting the other magnetic field coil, so they interact. And the result is that if you curl up a wire, it has the ability to store energy in its magnetic field. Okay, so, and they have the property that they resist rapid changes in current because it takes time for that current to build up into the magnetic field and then be released. So current changes tend to lag changes in voltage. There's a delay in response. That's how it's different than a resistor. When things happen with resistors, whatever happens to the voltage, it immediately happens to the current. But inductors, because they have to transition energy into a magnetic field, there's a delay. The symbol for an inductor in a circuit diagram is, it looks like a coil like this. And the letter is L, not really sure why for inductance, probably something to do with Latin, but I'm not really sure what it is, honestly. It's called inductance, and it's measured in a unit called henries. All these are named after, initial pioneers in electrical and charge theory. And then there's a third type of circuit element. There's really only three general types, and this one's called a capacitor. Capacitors are usually made of plates of metal like this, which is why its symbol looks like this. And then there's some kind of a non-conductive medium called a dielectric that prevents charge from moving between the two easily. Okay. Often the plates are flexible, so they'll take like like pieces of foil, and then they'll sandwich them in between dielectrics and then another piece of foil, and then they roll that up into a tight little ball here and they stuff it into a can, right, to make the element that has the leads sticking out of it like that. So but ultimately it's two electric plates separated by a dielectric. So what capacitors have the ability to do is if you try to put charge into one side in the form of a current, direct current can't flow through a capacitor. But what it does is it causes charge to build up in the space here. So it creates an electric field between the plates. So capacitors have the ability to store energy in an electric field, whereas inductors store it in the magnetic field. Okay, so yeah, they resist rapid changes in voltage for that reason because they have to charge up. So the voltage change actually lags the current. So they have these, so inductors and capacitance have the ability to change the phase between the current and the voltage in a circuit. All right, we don't need to know all of that to solve these things, but let's talk about how they relate to differential equations. So one of the simplest circuits you can make is called an LR series circuit. It has a single inductance and a single resistance in it. Right, so if you have that like that, where you go from the positive terminal of the voltage through an inductor and a resistor and then back to the negative, it will create current flow in this circuit. And it turns out that because of the way it's storing energy in the magnetic field, right, the resistance, the electric part just uses Ohm's law, E equals I times R. But you can add another element for this, but it's the rate of change of the current that causes something that's like a voltage drop across the I. So it turns out you need a differential equation to represent a series LR circuit. It's the inductance times the derivative of current with respect to time, how fast current is changing, plus the resistance times just the current itself equals the voltage. And this equation comes from the fact that the voltage drop across the inductor is proportional to how fast the current is changing, because it's trying to resist those currents changing as it's charging up its magnetic field. All right, so this is a linear first order differential equation. So we could solve equations like this using the techniques we know for first order differential equations that are linear. And then there's another circuit that we can use. We can take that resistance and combine it with a capacitor in series. And if we do that, it turns out that E is IR, but it's 1 over the capacitance times the charge itself that's being built up here. That's important, right? So because current is the derivative of charge, it's how fast charge moves past a point, then this I we replace with the derivative of charge with respect to t. So it ends up being that the resistance times the derivative of charge with respect to time plus 1 over the capacitance times the charge equals the electric field total that's being applied across the circuit. And so again, we have a linear first order differential equation that we can use to solve a simple 2-element circuit. All right, so that's kind of the main things we can do with first order linear equations, which are fairly limited. There's other things too, but there's kind of the general ones here. Another thing that might come up in your homework as you look at this is we're going to talk about how you can use a phase portrait to establish long-term and transient behavior. We've kind of talked about this before in the beginning of our studies here of chapter 2. Here's another example, a mathematical model for the rate at which a drug disseminates into the bloodstream. Okay, so that could be shown to be given by dx dt equals r minus kx, where r and k are both constants and x is a function that describes the concentration of drug in the bloodstream at time t. Okay, since this is an autonomous equation where it only contains the dependent variable over here, this x, r and x or r and k are constants, that means that we can draw a phase portrait, right? We solve for where this right-hand side is 0, which occurs when x is r over k. So if you draw a phase portrait for the dependent variable, which in this case is called x, not sure what we can call it, y or c or q, then there's one value here that splits us apart at r over k. And that means that the slopes above and below are either going to all be positive or all negative in either side. So to check that, what we could do is say, let's imagine that we have an x that's larger than this r over k. And I'm going to plug that in for this. So I'm going to plug some value that's larger than r over k in here into the right-hand side. So I have r minus k. So these k's cancel out. And I'm going to have r minus a value that's greater than r. And so therefore, this will be a negative value. So this slope must be negative for any x above this critical point. And conversely, down here, if you plug a value in that's less, then you're going to take r minus something that's less than r, which is positive. So we'll have positive slopes here. And that means that we could just use the phase portrait to get some idea of the curve behavior, right? The solution curves are going to always have positive slopes approaching that critical point as an asymptote as we move from left to right as time goes on. Or if you start out above that, it would go down, right? Which means that eventually, right, we're going to end up with a certain value of drug in the bloodstream, and it's going to be R over K, whatever these two constants are, their ratio. Okay. Now we could actually solve that equation using techniques. If we have dx dt equals r minus kx, right, we could move the kx term to this side to get a linear first order differential equation with px equal to k. We could solve this with an integrating factor, which would be e to the integral of k dt, which would be e to the kt. And that means that this times the dependent variable is equal to the integral of the right-hand side, which was just r when I rearranged it, times the integrating factor. And when you take that integral, you get r, and then this derivative is, or antiderivative is the copy, but divided by the constant. So you get r over k e to the kt plus an integrating constant c. And then if we apply a condition that when time is 0, the blood concentration is 0 in the bloodstream. So I'll plug in 0 for the blood concentration at time 0. We can solve, and we'll get that this c right here happens to be negative r over k. So if I fill that in, I'm going to get a term here which is just r over k. Let's see, x of t, here it is. Okay, so I've got r over k. Oh, sorry, there was one other step here I omitted, right? You have to divide both sides by this e to the kt. So when you do that, this cancels out and leaves r over k. And when you divide this by e to the kt, it's the same as if I move that up, e to the negative kt. So when you use this equation and plug in 0 and 0, you get that this c is negative r over k. So here's the final solution here. And what I want you to notice about this is that one of the terms includes an e to the minus kt. So when t gets large, as t approaches infinity, this value here drops off to 0. It's an exponential decay. So this term will fade out. And that means that that entire term over there, this term here, is referred to as a transient term because it's only there for a transient amount of time and eventually it leaves. Any remaining stuff that's still there in the long run is referred to as the steady state term or steady state terms. And if you were to graph this solution right here, I just picked a couple values for r and k, you'll get something that looks like this, right? We said we started here at 0. This will ramp up. And so for this part where things are changing, that's what we call transient behavior. It's still in the process of changing. But at some point when this term fades away, we subtract less and less and less until finally we get to this place out here, which is r over k, which is 2, which is the steady state or terminal value. So the system starts in a changing state, but over time, the effects of any term that's transient fade out and you're left with just the steady state solution. Okay. All right. Okay, so just to wrap this up, there are other scenarios that can be modeled with first order linear differential equations. For example, how materials flow between conditions where the materials are mixing. There's some very simple velocity and air resistance for falling masses in physics, but we typically use more complicated models for that we're going to talk about in 3.2, which are nonlinear. These scenarios have so many variations, there really isn't a standard form for them. So you would need to build the differential equation and solve it. But the general pattern will be this. You'll find a differential equation that matches the scenario in some way, solve that differential equation using a known method that results in a general solution with one or more constants, use the given conditions and information to solve for the constants to get the specific solution, and then use that solution to answer the follow-on questions in the problem. Right? All right, that's it for 3.1.